In the last video where we introduced the concept of magnetization, we said that this solenoid could make for a really good electromagnet, especially if you were to wind the windings of wire around a core made of some special type of metal. And ideally, that metal is not paramagnetic or diamagnetic, but to get the strongest effect, you want it to be ferromagnetic, which has something to do with once the current flows here, then the magnetic field of the windings of wire cause regions of the ferromagnetic material called domains to line up and point in a direction parallel to the magnetic field associated with the current loops. When that happens, you start with a chunk of metal that before the current flows in the wire, its magnetic domains are totally random and point in all different directions. These domains are formed when neighboring atoms influence one another and make their magnetic dipole moments add up. Okay, and then as the current is turned up and the external magnetic field, so to speak, I guess it's internal to the solenoid, but external to the chunk of iron. As that magnetic field, we'll call B naught, is increased, then the domains start to align a bit more, right? Instead of being completely random, they all have a component that points a little bit to the right in the direction of B naught. And as you increase the current and make the value of B naught, therefore, even greater, you get to a point where the domains are almost completely aligned, and then you reach saturation, and there's no more increase in external magnetic field that's going to make the iron have any greater magnetization, right? It reaches maximum magnetization value, which remember is the sum of the alignment of all the magnetic dipole moments of each atom divided by the total volume. So if the magnetic dipole moments are as aligned as they're going to get, then you've reached a maximum magnetization. So we can make a graph that represents how magnetization increases as the external field is increased. So maybe when the external field is of a value this large, it produces a magnetization that would plot at that point on our graph of magnetization versus external field. So then the question is, well, I might have gone a little too far. Let me back up a little bit. Magnetization and external field. So if we start in case number one, where it's totally randomized, then you have zero magnetization for the material, and then as the magnetic field is increased and increased even more, then eventually you reach saturation. So maybe this dot represents a point here where you're almost at the saturation. Now, if you wanted to bring the material back into a random alignment of domains so that the magnetic field falls back to zero, you'd think, well, then I just need to bring the magnetic field back down. But what happens is as you reduce the magnetic field to zero, the magnetization doesn't drop to zero. When the field strength reaches zero, there's still some lingering alignment of the domains. So what you would have to do is reverse the magnetic field in order to wash out the alignment of the domains, so to speak. So if you started with some positive magnetization, when the field, maybe we'll say a magnetic field pointing to the right is positive, and an external magnetic field pointing to the left is negative, then bringing the external magnetic field to zero keeps some magnetization, so you would have to create a magnetic field pointing back in the opposite direction before the magnetization reaches a zero value. Now, if you continue, if you make the external magnetic field even greater, then you can get the domains to start to align toward the left, right? And then as you keep going, you reach saturation in the opposite direction, and the domains are going to be as aligned as they get. So you get to maybe here. And then if you wanted to reverse it again and bring it back to here and then back to randomness, then the same thing occurs in the other direction. Oops. So what you end up with is a plot that might look something like that. And we refer to this shape as a hysteresis loop. And it's basically explaining that when you bring the external magnetic field to zero, now where's the external magnetic field zero? There and there. Zero magnetic field does not mean zero magnetization. The field always has to be brought either if I already had some positive magnetization, then if I want to bring the magnetization to zero, I need to make a field in the negative direction. And if I have some negative magnetization, then bringing the field back to zero doesn't make for zero magnetization. I'd have to make the magnetic field go back into the positive direction to bring the magnetization back to zero, right? Okay, so some materials have a hysteresis loop that looks like this. Whereas other materials have hysteresis loop that looks more like this. So if it has a really broad hysteresis loop, then that would make for a good permanent magnet. And if it has a narrow hysteresis loop, then that would make for a material in an electromagnet. This is basically saying you need really big reversals in the external magnetic field in order to bring the magnetization up and down, whereas something with a narrow hysteresis loop doesn't need as big of a reversal in magnetic field in order to cause big swings in the value of the magnetization. So it's really something that has a hysteresis loop in this shape would be very difficult to magnetize it in the first place, right? You have to introduce a really large external magnetic field to reach the saturation point. So it's hard to magnetize, but it's also hard to demagnetize. So once a material like this has been magnetized, it has a tendency to stay magnetized. Whereas material like this, you didn't have to bring the external magnetic field to such a large value to reach saturation. And so because of that, you don't have to reverse the magnetic field too far to bring the magnetization back to zero. So as soon as you turn the electromagnet off, it almost completely loses the alignment of its domains.